So what we'll do, Brian Winkle, when this keynote's over, we'll refresh this call before we jump into the Math Bowl. Is that okay?
Yes, that's fine. Okay, I think we're ready to go. You've been gracious, over 50 of you out there in the audience hearing this chat go on. Basically, we have Brian Macdonald, who has just made a move from ESPN as a data scientist to Carnegie Mellon University in Pittsburgh, and is teaching in the statistics and the business school. I first met Brian when he was a postdoc for teaching and research purposes at the U.S. Military Academy at West Point. The goal of the project is to help people develop a career in teaching, and he was a total failure because the first thing he did when he went out is he became the chief quant for the Florida Panthers NHL hockey team, which was not what we really envisioned. But what we envisioned is a talented young man who's been able to find his way around this incredible world of sports and data science. So I'm going to turn it over to Brian for the next section, and feel free to ask questions in the chat, and if we see an opportune, Brian would be glad to answer them, but we could also have questions at the end. So Brian, you're on.
All right, thank you, Brian, and thank you for calling me young man. Makes me feel younger, and I promise that I'll be using all of the things that I learned at West Point in my role at Carnegie Mellon. So yeah, let's get started here. So we're going to be talking about an overview of data science problems in the sports industry, and I'm also going to talk a little bit about why use sports analytics in education at all? Why use sports data in education, and what are the benefits? Just a little bit of background on me. Brian mentioned some of this already, but special faculty in sports analytics at Carnegie Mellon University in the Statistics and Data Science, at the Department of Statistics and Data Science. I was previously at ESPN as Director of Sports Analytics. I was at the Florida Panthers as Director of Hockey Analytics. I was at West Point. I would like to point out that I actually did teach differential equations a few times when I was there. So I have a little bit of experience, but it was a while ago. I was unfortunately the second best looking Brian in the department at the time, because as Brian Winkle mentioned, he was there at that time. So, and by, education is in mathematics, but kind of while I was at West Point, I sort of transitioned from mathematics to data science and kind of been doing data science ever since then. So just an overview of what we're going to talk about. I kind of already mentioned this, but why sports analytics in education? Then I'll talk about some data science problems in sports, problems that are interesting to teams, both from both business analytics problems and sports analytics problems. Problems that are interesting to media organizations like ESPN, leagues like the NHL or the NBA. And we'll actually talk a little bit about a system of difference equations at the end. And it's not differential equations, but it's close enough. And, beggars can't be choosers. That's as good as I could do as far as sports world. So let's talk about why sports analytics in education. So I listed a few reasons here. One of the big ones that there's tons of publicly available data that is free for anyone to use. The leagues have a lot of data. A lot of the data comes from their homepages. That's easy to scrape. There's already a lot of packages in programming languages like R or Python that allow you to, there's already functions written that help you scrape the data. So there's tons of data out there. There's a wide variety of data also. There's a wide variety of data and problems and methods that are required to solve those problems. And a lot of these problems are actually analogous to something that you would that would arise in other non-sports applications. So any experience that you gain studying these sports problems, it translates to other fields as well. And sometimes it's actually easier to learn about some of these methods using sports data, because sports is sort of like this controlled environment where there's a fixed, there's a fixed set of rules. The playing surface, the court or the rink or the field is a fixed dimensions. You can't go outside of the lines and things like this. So it's sort of like this controlled environment. And so sometimes things are more well behaved because of that than in the real world. So sort of getting up to speed in some of these methods using the sports data and then moving to somewhere else is sometimes helpful. Sports are also very widely popular. I mean, certainly not everyone likes sports, but we found this statistic that in 2019, 150 million people in the US watch live sports at least once a month. So what this means is that students, if they're learning data science techniques or whatever, linear matrix, algebra type stuff, they start out as sort of subject matter experts if you're talking about sports, because they've either played sports or they've watched sports. And this is helpful in a lot of different stages of, like a modeling process, including, one of the most important parts is sort of defining the problem up front. What are the most interesting problems to study? What are the most interesting questions to try to answer? And then, what are all the things that you have to consider when you're trying to answer these questions? So having knowledge of the subject that you're studying is useful. And it's also kind of nice that you can have real life validation almost immediately for some of your models. If you have a game prediction model, you can wait until tomorrow and see what happens in that game. So that can be kind of nice also. But let's get into some example problems. So we'll start out with some business analytics problems, and we'll go through these kind of quickly and get to the sports analytics problems. But one of the things that I worked on in the beginning of my time at the Panthers was predicting attendance. So an important question that organization has, if you're in the sales team, is how much demand is there going to be for a game? Because you want to know, what do you want to price that game at? So games are not all priced the same. So teams usually use, they'll price them differently because of who the opponent is. If it's a really big opponent, or if, depending on the day of the week, they might change the price. So we build a model for predicting attendance using a bunch of information like day of the week, month, opponent, whether or not it's on a holiday, things like that. We're going to kind of not show any of the results of that. Just wanted to give you an example of one kind of problem that sales and marketing is interested in. Another important problem is sort of like understanding your customers, doing some customer analysis. Who are they? Where do they live? Why do they buy tickets? So we collected, we used some of our internal sales and customer data. We got some US Census data, just scraping from the web, and Google Maps data for driving time into the arena. And we kind of merged it all together and plotted some maps. And so what we see here on the left is the dots are our customers, and they're full season ticket holders. And in the background, there's like a heat map, and that's colored by driving distance to the arena. And this is the arena right here. And so that we catch our bearings, this is Southeast Florida. This is Fort Lauderdale right here. This is Miami down here. Just the names are covered up by dots. So we're looking at the southeastern part of Florida right now. And so, so that's the left one. And then we have some US Census data here, kind of lined up in parallel with this left one. So this is the second one here is median income. The third one is gender. And this fourth one is ethnicity. And so, so we got some interesting insights by looking at this. Like, for example, most of the season ticket holders are in this greenish region here, which is very close driving time to the arena. So, but I mean, we could talk about this for probably a half hour, but in the interest of time, we're going to move on to realignment. So this is a problem that a league might be interested in. What realignment would minimize league travel? And so, in other words, how should we put teams and conferences and divisions so that their travel will be minimized. And this is important if teams in the same division play each other more often, then this realignment matters. And so this is a problem that we worked on. I guess this was when I was at West Point. I did this with a colleague of Brian and mine, Bill Pullyblank. And we developed this algorithm that basically used straight line cuts to split the league into 2 equal-sized conferences, and then formed conferences like this in the red and the gray. And then you can do the same thing for each of those conferences, use straight line cuts to cut those into equal-sized divisions, either 2 divisions or 3 divisions, whatever you want to do. And then that gives like thousands of possible realignment solutions. And then you can come up, we came up with a way to approximate league travel for each of those possible realignments. And you can sort all these 1,000 solutions by that metric. And so this is an animation that I think it just shows the first 10 best solutions. And so travel is certainly not, I'll go back to this one. Travel is certainly not the most important thing when you're typically thinking about realignment. Back when we did this, the team in Atlanta moved to Winnipeg, but they were still in the Southeast Division, which, at that point we knew the NHL was going to do some sort of realignment. So that's why we did it back then. Interestingly, this year, there was sort of another temporary realignment because of COVID. So all of the Canadian teams are in the same division this year because of issues crossing the border. And the other conferences are decided pretty much based on location. So they put the teams that are close to each other in the same division, essentially. That is a big consideration normally also, but the other thing that they consider is time zones. So because of TV ratings, they want to make sure the teams that are in the same time zone are in the same division, essentially. So let's move on to sports analytics problems. So this is the kind of problems that teams and media organizations are interested in. And so one of the big things that people work on is player ratings. And teams are interested in this because they want to evaluate player performance and player personnel decisions like trades and so forth. And media organizations like ESPN are interested in that so they can talk about those decisions. And so one of the metrics that we created at ESPN while I was there was the NBA real plus minus metric. And so this is a statistic for NBA players that estimates that player's individual contribution to his team. And there's offense and defense components. It's expressed in terms of points per 100 possessions. And one of the important things about it is that we have used a model that accounts for who the player's teammates and opponents are. And it's more important actually to account for the teammates. And basically that's because you don't want a player's rating to depend on, you don't want playing with really good players versus playing with really bad players to affect a player's rating. So you kind of want to account for how good their teammates are in any sort of model. And so we created this for all seasons back through 96, 97, which is how far back we had the data. And we can do comparisons like this. This is LeBron James and Giannis Antetokounmpo. Kind of shows, recently in the 1920 season, Giannis, that was the first year that Giannis was kind of overtaken. Well, I guess he's a little bit above LeBron there. But in the 1920 season, according to Real Plus Minus, Giannis contributed more to his team in terms of points per 100 possessions. And so that would say, Giannis deserved to win the MVP that year. And that year he happened to win the MVP. He also won it in this year where he wasn't the best player. But so that's player ratings. There's also team ratings. Teams care about this because they want to know, what's our season outlook look like? How likely is it that we're going to make the playoffs? And media organizations want to be able to say those things too. This team is very likely to make the playoffs, or is going to be right on the borderline. And then these team ratings can be used for a lot of other things also. They can be used to predict games. Those game predictions can be used in season simulations where you can get expected win totals or the probability to make the playoffs like we talked about. More recently, something that's becoming more and more important is betting metrics, like what's the chance that this team is going to cover the spread, something like that. That's becoming more important because betting is becoming more legalized in more states. So here's a visualization of the results of one of our models. I think this is our preseason model to before the NFL season this year. These are all the teams in the AFC along the left. These are the wins 0 through 16. And this just shows, for example, for the Chiefs, this shows how likely each win total is for the Chiefs. So we have them winning around 12 games, but sort of a range here between 9 and 14 or 15. So it's a nice way to get a snapshot of like the most likely outcome for a team, but also how wide is the spread? What is the variance in the outcome of their season? Another project that we worked on when I was there is another guy on our team built NFL draft projections. So the NFL draft is an event where pro teams can select or draft college football players that are eligible to be taken. And when it's their turn, they can choose either the best player available or whatever, or whoever they think is the best player available, or they pick, who is best meets their needs. But one thing that we wanted to do so that we could talk about and project what might happen in the draft is build a model that estimates for each player and each pick the probability that a player will be selected at that pick. And then you can answer questions like, how likely is it that player A will be available at pick X, and things like that. And so here's a visualization of the results of the model. This is one player, Tua Tagovailoa, who was one of the top prospects in the draft. And the model didn't think he was likely to be taken in the first 2 picks, but it thought the 3rd pick and the 5th pick were the 2 most likely spots that he'd be taken. And it probably thought this team picking at number 4 did not have a need at quarterback, so it wasn't he's a quarterback. So it probably thought that they didn't have a need at quarterback, so they were less likely to take him in the draft. So that's why it's not kind of like smooth here. It kind of dips down at 4 and comes back at 5. The other nice thing about this model is it was easy to update as picks occurred during the draft. So here's an animation kind of showing that as picks happen, as the first pick happens, he becomes 0% chance to be selected at that pick, because that pick has already been made. And you see all the other probabilities update as time goes on. And then he was actually picked at pick 5, so that's why it shoots up to 100% there. This is another way to sort of visualize sort of more results from this model. So this is 10 of the top players in the draft. These are picks 1 through 10. And what we're seeing here is the likelihood that each player will be selected at each pick. So Joe Burrow was pretty likely to be the number 1, Chase Young, number 2, and so forth. Here's Tua. He has got the peaks at 3 and 5, like we saw before. And we can update this also. So this is a fun animation. This is actually showing 64 players and the first 64 picks and how these probabilities update over time as players are chosen. So a lot of the players are along diagonal here, in the range that we kind of expected them to be picked. But then there's a couple squares that show up down here that are like, these are the players that are selected much earlier than we expected that they might be selected. And so it's kind of a nice way to sort of visualize some of the outliers in the draft. All right, so we'll get to player tracking data now. So this is sort of considered like the cutting edge of sports analytics now. Most of it uses player tracking data. And so these are player and ball locations several times a second throughout a game. And This data is collected either by camera-based technologies or chip-based technologies. In the NFL, players have chips in their shoulder pads. So using this technology, basketball, it's cameras. Using this technology, you can get player and ball locations many times a second throughout a play. And so this spatial temporal information is really important for analyzing plays. A lot of the data that existed before told you about outcomes. How many points did someone have, or rebounds or whatever. So they tell you about final outcomes or of a game, or a final outcome of a play, or a final outcome of a possession. But understanding what happened throughout the duration of a play or a possession wasn't possible with that data, but it is with this data. And so here's sort of an animation of this data. This is the offenses in blue, the ball is red, and the defense is in gray. And we can kind of just see what this data looks like if we plot it as an animation. And so what do people do with this data? So a couple examples are related to expected points. So given the locations of the players in the ball, what is the expected number of points the team will score in the current possession? And that was the work here of Dan Cervone et al. And I can get you links to any of this stuff afterwards if you're interested, but you can also Google Cervone expected points and find this. So as given the locations of the player and ball, as the play develops, what is the expected number of points the team will score in the possession at any moment in the possession? Another similar question is, what is the probability of a field goal attempt, or a shooting foul, or a non-shooting foul, or a turnover, or none of the above? What is the probability of any of those occurring within the next 5 seconds? And so that was a question that Cecilia Pellegrinis and Goldsberry looked at. If you Google deep hoops, you can find that paper. And this is similar. You can actually get expected points from looking at these probabilities, but it's a little more granular than looking at expected points. And so this next animation is based on their work. So at the top, we have the moving dots again. We see here expected points at 0. They're just bringing the ball up court. So the expected points in the next 5 seconds is 0. But then it starts going up and down as they start executing plays in the offense. And at the same time, we see the probability of field goal attempts, the probability of turnover, probability of none. All these things are changing throughout the duration of the play. At the beginning here at the bottom, none is 99% or 100%. So no event in the next 5 seconds. But then once they start doing stuff, those probabilities all change. And so what you can do is you can assign credit or blame to players for certain plays, like little micro plays that happen within a possession. These little micro actions. These can be evaluated based on a model like this. How does it affect the expected points? How does this particular little micro play affect expected points? How does this pass from one player to another change the expected points? And so similar thing can be done in football. So we can talk about expected points in football. The first step there is finding expected yards at the end of a play. And that was the work. This is something that Ron Yurko et al. Worked on. You can find this by Googling Yurko going deep. And here's an animation that shows this. The other thing that they did, this horizontal line is the expected end of play yard line for this play. This is a touchdown run by Leonard Fournette. But what they also did is they had the expected yard line, but they actually got a full probability distribution, which is shown on the left here, of all the possible outcomes of a play and how likely these outcomes are to occur. So you see at the beginning, there's kind of like 2 humps, one at 30 and then one at the goal line. And as the play goes on, as he moves past the defenders, this bubble down here kind of goes away, and the huge peak, there's a huge peak at the goal line. And the peak at the goal line means he's going to score a touchdown. So once he passes this defender here, right around the 50-yard line, this peak shoots up. It's just saying the most probable outcome of this play is now a touchdown. And so the same kind of things you can do here. So all these micro actions, there's these mini plays within plays you can analyze based on how they change expected points, or expected yard line, or expected points, the same thing. And having the full distribution is nice because you don't just have the expected yard line, you have sort of a measure of variance, like how wide is the range of possible outcomes for this particular play. Like at this point, it's a very wide range. And you can find more about these last two things with the player tracking data in an article I wrote, like a review article recently. You can find it by Googling HDSR Macdonald, but it has more details on these kinds of things. And then the final thing that I kind of wanted to talk about was this example of modeling offensive player movement. And this is where we get to start talking about difference equations. And so this is work by Stephen Wu and Luke Bourne. You can find it by Googling Wu modeling offense. But this is a really nice paper because it's a really accessible overview of this problem that would be pretty accessible to undergrads. And they provide code and example data for this also. These are linked in the paper. You don't have to remember this whole URL. It's linked in the paper. But what they do is they model a player's movement on offense in the short term using equations like this. So X, X and Y look pretty much exactly the same. So X position at t+1 is their position at t plus some constant times the position at t minus position at t minus 1. So this is like velocity. And then they have another term here that's like a higher order term. And this is estimated using data. And this is different for every player. And one of the cool things they do in that paper, which reminded me of my days teaching ODEs, is they visualize acceleration vector fields for every player. So here's LeBron James, and this is split into when he has the ball and when he does not have the ball. And so we see the vector fields of, if he gets the ball in this location, well, he's most likely going to be pointing towards the basket and going towards the basket. But player vector fields can look pretty different from one another. So this is Andre Drummond, and you notice his looks pretty different over here. This is basically because he's a big man. He's a center, and he's not going to be running down the wings or anything to try to get an open three-pointer. He's just going to be going directly towards the paint area as quickly as possible. So that's kind of why that shows up there. So we talked about a lot of examples here of sports analytics problems in data science. Things that are examples of solving real-world problems, joining data from multiple sources, lots of visualization. A lot of these require students, if they're working on them, to get experience with multivariable thinking, not thinking it's this variable and that variable. Well, there's actually n variables involved in this problem. A lot of experience modeling, interpreting models, and so forth. And most of this data, some of these projects used proprietary data, but in almost all cases, there are publicly available alternatives to the stuff that I showed here. And so, couple initiatives that we're involved with at Carnegie Mellon is this. We're starting to build a network called the SCORE Network, which stands for Sports Content for Outreach, Research, and Education. But I guess the best way to describe it, it's almost like SIMIODE, except for it's for sports analytics and data science, essentially. So we're creating a lot of resources. We're partnering academic partners and industry partners and media partners to create content and disseminate content to faculty and students around the country. And we've kind of have some confirmed partners here in this map and a few initial hubs. One of them is a New York hub, which involves West Point and St. Lawrence. There's a Carnegie Mellon hub, and there's a Texas hub at Baylor. So So if any of this sounds interesting to you, is something like you might want to be a part of, please reach out. Other things that you might be interested in, or your students might be interested in. Carnegie Mellon has a summer camp for undergraduate students who are rising juniors or seniors. They get hands-on experience in data science using sports data. They get a stipend to cover living expenses, so they're not paying for this camp. They're getting paid as like an intern to go there, and they get research experience. It's like a summer research experience. There's also a conference. The date is not set yet, but there's a conference in fall, and there's the conference website for the 2020 conference. So if you have any interest in doing any of those things, feel free to go to those websites or contact me if you have any interest. But I think I am out of time, so we'll end there.
Yeah. Are there any questions? We have one question that said expected points or averages. Are the averages taken over teams, the leagues, the position? I mean, is that a...
Yeah, so the expected points that we were talking about, those occasions were based on the locations of the players and the ball and their trajectories, basically. So based on position and velocity of the ball. I believe in those two studies, they weren't using the identity of the player, but you could build a model that uses that as well.
Yeah, can this work be used to develop better player strategies?
Yeah. So the animations that we showed and the sort of the analysis of how expected points goes up and down, that could alter what kind of plays you run. If a model might be able to tell you, hey, this play, this pass from here to here, it wasn't very effective. Maybe you should try to do something else.
And I guess a related question is, do the clients, which are maybe team owners and players, how do they respond to all of this? They have to be educated like that, watching that animation. I think you could see things, but maybe there are more subtle things, right?
Yeah. I mean, I think I would say the way people react to it is highly dependent on the organization. There are organizations that rely on this stuff heavily, and there are organizations that don't do a whole lot of this kind of thing. So it definitely depends on the organization. And anytime you're talking about something new or some new way of thinking about things or analyzing a problem, there's some change management that has to happen somehow. So that's definitely a challenge for a team. Also for ESPN, an organization like ESPN, like the on-air hosts want to understand the things before they say them over the air, for example, or the producers want to make sure they understand what's going on.
And how many data science were in the NHL when you started with the Panthers?
That's a good question. Thinking back, maybe there were 3 to 5 people when I was hired.
Okay.
I would say now there's probably, and I haven't counted recently, but maybe 15, 12.
Okay.
10, I don't know.
Right.
But it's definitely growing in sports. It's grown a lot in the NFL the past couple of years because the player tracking data just became available. And they have a competition called the Big Data Bowl, where students have been able to showcase their skills, and teams have hired, winners of that competition, essentially.
Okay. Well, we need to stop because we're going to get on to a game of our own called the Math Bowl. But let's thank Brian for his sharing it. I think I had more questions, and also, NBA players wearing chips on their shoulders, all kinds of tracking of motion, and it seems exciting. And I'm glad you're able to come back to academe and at the same time keep your hand in the game. So thank you very much, Brian. We'll close this session. Yes,
appreciate it.
good to talk to you.